Today we're doing some more Calculus 2 practice problems, and we're looking at infinite series. So in the last video we looked at sequences, which have a first, second, third, and nth term. And all we're doing with series is adding up those terms. So this is what it looks like in sigma notation. We are adding up that sequence of n terms from n equals 1 to infinity, and that becomes s sub n. So a little bit of notation, s sub 1 would just be the sum of the first term, or just the first term. S sub 3 would be the sum of the first three terms, and finally S sub n is the sum of n terms. Right, so let's look at the first kind of series that we are going to do in the next few videos, called geometric series. A geometric series has this form. It's the sum from, this is important, n equals 0 to infinity. It has to be from n equals 0, at least to converge to this quantity, which we will look at. But ar to the n power, so this is n1, right, because we have r to the 0, right, r to the 0, and r to the 0 is just 1. Then we have ar1, ar2, and we're going to add all of those up to ar to the nth power, right? So does this converge? Well, what does it mean for a series to converge? In the last video, we looked at sequences converging, and what it meant for sequences to converge was that the terms were approaching a certain number. For example, 1, 1/2, 1/4, 1/8. These terms are approaching, getting closer to 0. So what does it mean for a series to converge? All it means for a series to converge is that its terms, or the sum of all the terms of this series, approach a finite value. So does this geometric series converge? Yes, it does, but only on one condition. The absolute value of r must be less than 1. That means r right here must be a fraction or decimal in between -1 and 1. So it can be negative. It just has to be less than or equal to 1, or the absolute value. Right, so to what does it converge? I'm not going to prove it in this video, but this will converge to a over 1 minus r. And we'll look at this in the next few examples, and we can also look at what this means intuitively. So this is the first kind of series we're going to look at. But before we get started, I want to note that most series diverge, and we're going to look at that with the divergence test at the end of this video. But most series out there will diverge. We're just looking at a few in this video that happen to converge, and then the next 5, 6, 7 videos will just be about how can we determine whether a series converges or diverge. So let's look at the first example. Does this series converge? And remember, converging means it is approaching a finite sum, or its sum is approaching a finite number, I should say. So you may not recognize this as a geometric series first, because we don't really see an ar to the n power, right? We don't see this, but it's there. You just gotta do a little detective work. First, we want to make sure that we're starting at n equals 0. That's important. We'll look at an example when it doesn't and what we have to do to get there. But n equals 0 to infinity. Isn't this the same as, well, 1 to the n power is just 1, right? So we could manually put this n here, because no matter what power that is, besides infinity, right, it's just going to equal 1. So we have that, and we technically have a 1 out front. So really we could rewrite this series as 1, and now if you have the numerator and the denominator to the same power, you can bring that power out of the fraction. So you can see we have an a, r, and an n that we need. So it wasn't there at first, but we were able to recognize it is a geometric series. So does this series converge? Yes. So we might have to do a little bit of writing on this last test. Most Calculus 2 sequences will end with sequences in series, and we might have to do a bit of writing on this test. We're going to say yes, the series converges. Yes, the series converges because we have to state why it converges. Because the absolute value of r is equal to 1/2, right? We have to check that first. The absolute value of r is 1/2, which is less than 1. That's usually, we can stop there in the next few videos, but with geometric series, we actually know what it converges to. For a lot of series, we won't be able to know what it converges to. We will just know that it converges. It converges to a over 1 minus r. In this case, a is 1, and r is 1/2. So we get 1 over 1/2, or 2. So at this point, so the answer is 2. That's what it converges to. But at this point, you may be wondering, like, what does this really mean? What does this really mean? That means we're going to, well, first we could look at the terms, right? What are the terms of this series right here? Let's see. If n is equal to 0, I'm just going to write out a few terms. If n is equal to 0, we get 1. If n is equal to 1/2, we're going to get 1 times 1/2, or 1/2, and this process repeats. And we are adding all these up, and apparently if you add these up as you go to infinity, we get 2. So we can also represent this with a picture. If we take this box with area 1, and we add it to a box of area 1/2, right, and add that to a box of area 1/4, and add that to a box of area 1/8, and you repeat and repeat and repeat and repeat, that's just going to equal 2 boxes. So that's how you can represent a geometric series intuitively. So let's look at another example. Prove convergence or divergence. So it's in our form already, ar to the n power, right? But there's an issue. What is the absolute value of r? It is 4/3, which is bigger than 1. So you'd say the series diverges because the absolute value of r is equal to 4/3, which is greater than 1. That's all you have to say. You would probably end up writing something similar to that on the test. So how about this problem? Prove the convergence or divergence of this series. So we're ready to go, right? A, r, n power. A over 1 minus r, 2 over 1 minus 1/2. So 2 over 1/2. So 4? No, this is not correct. Why is this not correct? That is not correct because we did not start from 0. We have to start from 0. So how can we alter this series so that we start from 0? Well, we can just put it there and just change the n. We can add a 1 here. So now when we plug in 0 for n, the first term we're going to get is really 1/2 to the 1 power, which is the same over here. So this might not make sense yet, but let's take this series, right? We don't know, or they are equal, but say you're confused about why they're equal. Let's list the first 3 terms of this sequence. And let's also list the first 3 terms of this sequence. Let's make sure they're the same. So the first 3 terms of the sequence on the left would be 2 and 1. Oh, this is not the first term, right? Because we're starting from 1. So it would be 1, 1/2, and 1/4. And the first 3 terms of this sequence are 2 times 1/2 to the 1 power, right? If you plug in a 0 for n, the first term you're going to get is 2 times 1/2 to the 1 power, which is just 1. And when you plug in 1, you're just going to get 1/2. When you plug in 3, you're just going to get 1/4. So you can see that the same series, all we did was have to add this n plus 1, right? But it's no longer in the form ar to the n, right? This is the series n equals 0 to infinity of ar to the n plus 1. So what can we do to get that back into ar to the n? Well, we could just do a bit of algebra and write this as ar to the n r to the 1, right? Because can't we just combine this into this so that we can work backwards a bit and write our, in particular, our series as that a to the rn times r1, or 2, that's a, 1/2 n times 1/2. Okay, so we can also take that 1/2 straight out of the series, or we don't have to do that because, lucky for us, the 2 will just cancel with the 1/2. And now we have the series a, which is now 1, r to the n. So this is going to turn into a over 1 minus r, or 1 over 1 minus 1/2, or 2, right? Just like the series that we looked at earlier. So if we had done this at first, starting at n equals 1, we would have an extra 2 in here, which would cause our answer to be 4. So we have to modify the series. And this may or may not come up in your lecture. It just happened to in mine. It's a cool little application. Speaking of cool applications, let's look at this one. Using a geometric series, determine how the repeating decimal, 0.63 repeating, can be written as a fraction. So how on earth can we write this decimal as a fraction? It's not 63 over 100, right? Well, here's how we should think about this. We could represent this fraction, right? 63 keeps on repeating, as 0.630000 repeating, added to 0.006300 repeating, added to 0.000063, and so on, and then so on. Right? Isn't this valid? Because if you were to add these three up, you'd get a 6-3 and a 6-3 and a 6-3, and you could keep going on for infinity. Now what I want to do is rewrite this in their fractional forms. 63 over 100 plus 63 over 100 squared, right? Now we're 4 zeros away. Finally, 63 over 100 cubed, and we're going to keep going. Finally, I want to factor out the common 63 over 100 from all these terms. And we have a 1 plus 63. Instead of 2 100s, now we're just left with 1. And instead of 3 100s, now we're just left with 2. And those keep going on, right? So we can actually represent this, or at least this part, with a series, right? This would be kind of like n equals 0, n equals 1, and so on. Right, so let's do the sigma notation. Starting at n equals 0, 63 over 100, and we're going to infinity. Right, that's what this dot 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 means. How can we represent all of this as a fraction? Isn't it just, if we were to keep going, as these dots suggest, isn't this just 63 over, oh, you know what, but we took out all these 63s. These are not here. We already factored out that 63, so we're left with this. Isn't this just 1 over 100 to the n power? And we can manually put the 1 there. So doesn't this thing, or I'm sorry, manually put the n there, so then this thing just turns to 1 over 100 to the n power. So everything that was in this parentheses right here can just turn to 1 over 100 to the n power. Isn't this a geometric series? So if we want to see what this decimal will become as a fraction, isn't this just a geometric series where r is, the absolute value of r is less than 1, so we can continue. And I'm going to skip the formality of saying like, yes, this is a geometric series because the absolute value of r is less than 1. We can skip that formality from now on. But a was 63 over 100. 1 minus 1 over 100. We have 63 over 100 over 99 100ths. right? So we can cancel out the 100s. So really, this crazy decimal right here just turned into the fraction 63 over 99 if you sum up all of these terms, right? If you punch this into a calculator, it will give you 0.636363 repeating. So kind of a cool application that we can do with geometric series. Once again, this may or may not come up in your lecture. Let's look at the second kind of convergent series. So once again, most series will diverge, but geometric series converge, telescoping series converge. We'll also look at one more after this, but telescoping series are series that can be broken down with partial fractions. So if you are not familiar with partial fractions, or maybe you forgot it being this late into the semester, I have a video on that and you can go back and watch it. But we're able to separate this product or this quantity into two separate fractions. But how does that help us determine whether it converges or diverges? Well, bear with me as we write out a few terms. Notice that these ones start from n equals 1, and most series do. Geometric series are just weird and start from n equals 0 because of the box thing that I showed earlier. But let's look at n equals 1, and let's write out a few terms. So let's start with n equals 0, or not 0, 1, right? N equals 1, n equals 2, n equals 3, n equals 4, and maybe even n equals 5. So let's punch out these terms. When we plug in 1, we're going to get 1 minus 1/5. We're adding that to n equals 2, which is 1/2 minus 1/6, 1/3 minus 1/7, and 1/4 minus 1/8, and finally 1/5 minus 1/9. So why is it helpful to look at all these terms? Well, notice that this negative 1/5 right here, after a few more terms are written out, will cancel with this positive 1/5. That's interesting. Let's look at n equals 6. We're going to get a plus 1/6 minus a 1/10. And let's see, this negative 1/6 will now cancel with that positive 1/6. So what's going to happen is this 1/7 will cancel with the next term. The next term will have a 1/7. This 1/8 will cancel with the term after that. And this 1/9 will cancel with the term after that. The 10th will cancel with the term after that. And all the other terms will cancel all the other terms. We're just left with these 4. And remember, what does it mean for a series to converge? A series converges when the sum, the infinite sum of all its terms, approaches a finite number. Well, if all the terms after this and towards infinity cancel each other, and the only things that are left with are these 4 numbers, then that must be what the series converges to. So it converges to 1 plus 1/2 plus 1/3 plus 1/4. And we can write that with the common denominator of 12. We have 12 over 12 plus 6 over 12 plus 4 over 12 plus 3 over 12. Finally, we have 18, 22, and 25 12. So that is what the series converges to. And technically, with those 4 terms, we do have a few more terms. You have to think about them in there. Like in nth term, we have a few more over here that survive, but as you go towards infinity, they get knocked out, right? Because you're dividing by infinity. So while we're proving convergence, your professor may care that you pay attention to the 4 surviving terms. In this case, there's 4 because these 4 survived, which means 4 more at the end, right? Must have survived. But they get knocked out as we look towards infinity because we're dividing by infinity. So we really only care about the first 4 terms. So that's how telescoping series work. So go watch the partial fractions video if you need a refresher on how to do this. But all that we're worried about with telescoping series is seeing which terms will knock each other out. right? So that's pretty straightforward. We can also look at the divergence test. After that, we'll look at the third kind of convergent series. So a divergence test, this is important because it should be the first thing that we do when we're given a series. If we're given some series like this, if the limit as n approaches infinity of a sub n does not equal 0, the series must diverge. What does that mean? That means if the nth term of a sequence, or like the infinitieth term of a sequence, does not equal 0, the series must diverge. So this is why most series diverge, because surely most sequences do not approach 0. So, for example, if we're given this series, and then we're asked to prove convergence or divergence like we did at the beginning of this video, we can just take the limit. This is a new strategy. This is not convergent, or I'm sorry, this is not geometric or telescoping. So we have to use a different technique. We're going to use this divergent test first always, because it's pretty easy. Let's take the limit as n approaches infinity of that sequence. What's happening with the infinitieth term? Well, you can either do L'Hopital's rule and get 1 over 1, which is 1, or you can, in the last video, we looked at something called n to the n FEPL, which is kind of a shortcut when we're dealing with limits. So this n and this n kind of cancel each other out as we look towards infinity, and this 1 is insignificant, right? So then we're just left with 1 over 1. What you'd say is, like I mentioned earlier, we have a formality. You'd say the series diverges because, this is what you would put on your test, because the limit as n approaches infinity of a sub n equaled 1, which did not equal 0. So it diverges by the divergence test, right? And it's important to note that if the limit equals 0, it does not mean that the series converges, right? It just means that the test is inconclusive, and we will have to use other tests. So in the next few videos, we will look at the integral test, the limit, comparison test, ratio test, root test. We have a lot of tests to determine whether a series like this one will converge or diverge. And that is pretty much what this entire section is about. So let's look at an example. Does the series converge or diverge? Just like the questions they asked with geometric. So first I'm going to kind of see, does it look like a geometric? No, not really. Does it look like a telescoping? Not really. Well, let's check if it's divergent right away. Be done. Limit as n approaches infinity of n over 2n plus 3. This 3 is kind of insignificant, and those n's cancel each other. The limit is equal to 1/2, which does not equal 0. So it is divergent. And you'd have to maybe write out the formality like I mentioned. So we just use the divergence test to prove that this series is divergent. Let's look at another one. Does the infinite series converge or diverge? So for this one, the limit as n approaches infinity of 1 over n equals 0, right? So inconclusive. Well, the test is inconclusive. So, how can we determine if this is convergent or divergent? Let's look at this one real quick. What is the limit as n approaches infinity of 1 over n squared? Once again, it's 0. So for both of these, they are, or the divergence test is inconclusive. So how can we prove convergence or divergence of these? Well, this one's divergent and this one's convergent. But why? It's something called a p-series. So this is the third kind of convergent series, a p-series. A p-series has this form. It is 1 over n to the p. So if p is greater than 1, the series converges. It doesn't we don't know. So this is the first kind of test. We don't know what it converges to, like with geometric or telescoping. We don't know what it converges to. We just know that it converges, right? And we can't really figure out what it converges to. You wouldn't see that on your test. So if p is greater than 1, this series will converge. If p is less than or equal to 1, this series diverges. So for example, this series would converge. This series diverges. This series converges because p is greater than 1, right? This is p right here. This is p. This is p, or there's an imaginary 1 right there. So since, in this case, p is less than or equal to 1, the series diverges. So we can look at these. We could rewrite this as the series of 1 over n to the p, where p is equal to 1. So you'd have to once again do the formality, it diverges, blah, 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 because p is less than or equal to 1, so it diverges by the p-series test, right? So this one diverges. But this one, it converges, right? It converges because p is greater than, well, we can write it like this. P is equal to 2, which is greater than 1. So it converges by the p-series test. So p-series, telescoping series, and geometric series are kind of the only series where we can quickly see if they converge. From here on out, the section gets pretty challenging. So let's look at this one. Prove in 2 ways that the series diverges. Well, we can tell if it diverges by looking at the limit as n approaches infinity of a sub n, right? This is a sub n, this is a sub n. We can see that we're just going to get infinity cubed with direct substitution. So because the limit equals infinity, that's not a problem. We like to see that actually, because we can just say that infinity does not equal 0. So it diverges by divergent test. There's the formality coming back again. What's another way we can do this? Now that we have that p-series knowledge, can't we rewrite this as, can we rewrite this as 1 over n to the negative 3? Because couldn't we just flip that back? These are equal to each other, right? So you could say that this is a p-series where p is equal to negative 3, which is less than or equal to 1. So yes, this series diverges. So we have a lot of this kind of stuff, kind of the proof of why it diverges or converges. So for n cubed, and that makes sense, right? If you were to write out the first few terms, you'd get 0, 1, 8, and you're adding that up. You can see that towards infinity, it's not approaching a finite sum. That really only comes with fractions. It just keeps getting bigger and bigger and bigger. This series keeps getting bigger and bigger and bigger, so it's not going to converge, right? It diverges, and we prove that with 2 ways. In our final example, we're going to look at proving the convergence or divergence of this series, but they didn't give it to us in sigma notation. They're making us do some technician work, right? This is n equals 0, n equals 1, or not n equals 0, right? That only comes from the geometric series. And this one may be geometric, but it's not, but we can look for that too. So this is like the first term, second term, third term, fourth term. How can we prove convergence or divergence? Well, we should probably write it in sigma notation and see if it's something we know, right? Isn't this kind of the same thing as, looks like all the terms have a cube root and a 1 on top, but what's changing? This one should have 1 too, but maybe it's just 1. Because the cube root of 1 is 1, and 1 divided by 1 is 1, this is the only part that's going to show up. But we can manually put that there to see the pattern. We can also manually put a 2 here to see the pattern. Isn't this just 2 squared? Isn't just 3 squared, 4 squared, etc.? So can't we just call this 1 over the cubic root of n squared? Does that work? I think it works. Because as n is 2, you get a 4 there, n is 3, n is 4. Right, so this is what we're calling a sub n. So this is 1 over cube root. We're going from n equals 1 to infinity. So it's not a geometric series. This is probably the first example so far where we're going to try and figure out what it is, or figure out if it converges or diverges. So let's start with, well, we should always start with, is it geometric? Is it telescoping? No and no, right? Let's start with the divergence test. Limit as n approaches infinity of a sub n. We're just going to get 0, right? So the test is inconclusive. Inconclusive. We're going to have to realize that this is the same thing as 1 over n to the 1/3 power, right? So yes, this series is a p-series. So it converges because p is equal to, no, it diverges, right? Because it's less than 1. P is equal to 1/3, which is less than or equal to 1. So it diverges by the p-series test. Right, so I almost messed up there. This is p, right? And if it's less than or equal to 1, of course 1/3 is less than 1, the series will diverge. So we looked at, to recap, we looked at geometric series, and we know what that converges to. We looked at telescoping series. We know what that converges to. We looked at p-series. We don't know what it converges to, but we can easily see if it converges or not just by looking at the number. And we also looked at the divergence test. So we should always kind of look at these 4 things first when we're given a series. Unfortunately, for the rest, the next 5, 6, 7 videos will be a bit tougher, and we're going to have to strategically choose a test that will allow us to determine if the series converges or diverges. But that is an intro to infinite series, right? Not too bad.